Tonight, our journey takes us toward a concept that seems simple on the surface, yet it stands as one of the most profound and challenging ideas in all of science. We will be exploring the light year. This is a term you have likely encountered countless times, as it is a fundamental unit for scientists discussing the cosmos. The intriguing detail, however, is what happens when you truly begin to understand its meaning. When you can fully appreciate the scale a light year represents, your entire perspective on the universe can shift. It is not merely a large number, it is a measure of distance so immense that it pushes the very limits of human comprehension. By the conclusion of our exploration, you will see precisely why astronomers rely on this measurement and why no other unit is truly adequate for the task. Before we proceed, if this type of deep, reflective exploration is something you value, your support through a subscription greatly aids our work. It is a simple action for you, but it makes a profound difference for us. Now, let us begin. We can start with something deeply familiar to us all: distance. You have an intuitive grasp of distance in your daily life. You comprehend the separation between your home and the grocery store, your place of work, or the next town over. These are scales you can relate to because you have experienced them directly. You possess a sense of what they imply in terms of time, effort, and the sights you might encounter along the way. A kilometer, for instance, is roughly the distance one might walk in 10 to 12 minutes at a comfortable pace. Such measurements are perfectly suited for the world we inhabit. If you are told a destination is 5 kilometers away, you can mentally calculate the approximate time it would take to drive. You can visualize the path in your mind. Perhaps you will pass several intersections or familiar buildings. The distance feels tangible and concrete. If a city is said to be 200 kilometers away, you can plan accordingly for the trip. This might equate to about 2 hours on the road. You would likely ensure your vehicle has enough fuel and perhaps pack some refreshments. You might even plan for a stop to rest midway through the journey. These distances are built on a human scale. They integrate seamlessly into our lives and our direct experiences. Our minds have evolved to understand the distances we can cover in a day on foot, the distances we can see with our own eyes, and the distances that are critical for navigation and survival. However, these familiar units begin to feel clumsy when we confront truly vast expanses. The distance separating New York and Los Angeles is approximately 4,500 kilometers. This is still a number we can manage conceptually. It represents about a 5-hour flight, a journey people undertake regularly. They traverse an entire continent. They witness the landscape transform from the urban density of the East Coast to the open plains of the Midwest, then to the rugged Rocky Mountains, across the southwestern deserts, and finally arriving at the Pacific. The journey is long, but it remains achievable. It is well within the scope of human capability. You can imagine yourself making such a trip. The circumference of our own planet at the equator measures about 40,075 kilometers. While this is a very large number, it is still something we can process. Early mariners circumnavigated the globe, proving that traveling this distance is possible, even if it required months of effort. The expedition of Ferdinand Magellan, for example, took 3 years to circle the Earth, from 1519 to 1522. In our modern era, commercial aircraft could theoretically complete the same circuit in around 45 hours, assuming perfectly connecting flights. The Earth is certainly large from our vantage point on its surface, but it is not incomprehensibly so. It is a finite sphere that one could, in principle, explore in its entirety. But now, let us expand our scale further. The distance from the Earth to the Moon is about 384,000 kilometers. It is at this point that our conventional measurements start to feel insufficient. 384,000 kilometers. This is a figure that is difficult to visualize in any practical sense. It is not analogous to driving across a country. It is not like sailing around the world. It represents something entirely different. There are no roads to follow, no landmarks to guide the way, and no places to rest. There is only distance, pure and simple, stretching across the vacuum of space. How could one even contemplate crossing such a void? The Apollo astronauts required about 3 days to travel from the Earth to the Moon. They were propelled by powerful rockets, which accelerated their craft to speeds of about 11 kilometers per second. This is equivalent to roughly 39,600 kilometers per hour, a velocity nearly 400 times faster than typical highway speeds. Consider that for a moment, a speed 400 times greater than any you have likely experienced. And even at that staggering velocity, which demanded some of the most powerful engines ever constructed and consumed vast quantities of fuel, the journey still lasted for 3 days. 3 days spent moving through empty space at speeds no human had ever before attained, just to arrive at our closest celestial companion. And this is only the Moon, the nearest natural body to our planet. The Moon is so close that you can observe it clearly with the naked eye. With a simple pair of binoculars, you can make out details on its surface. It hangs there in our night sky, a familiar presence, and yet it requires a 3-day rocket voyage to reach it. When we begin to consider the distances to other planets, to our Sun, or to other stars, the kilometer becomes utterly impractical. The numbers grow so immense that they are stripped of all intuitive meaning. They become little more than abstract symbols on a page, disconnected from any distance you can truly relate to. The separation between the Earth and the Sun is approximately 150 million km. Try to form a mental image of that. It is impossible, isn't it? Your mind simply registers it as a very large number, but there is no intuitive feeling for what it represents. Nothing in our daily experience prepares us for a scale like that. Nothing in our evolutionary history has equipped our minds to think in terms of such distances. We evolved to understand the path to the nearest source of water, the range of our hunting grounds, or the area we could traverse in a single day. We did not evolve to comprehend 150 million km. The Apollo spacecraft that carried astronauts to the Moon moved at an average speed of about 11 kilometers s. At that same velocity, a trip to the Sun would take about 160 days, which is more than 5 months. The fastest vehicle humanity has ever launched, the Parker Solar Probe, can reach speeds up to 192 kilometers per second as it nears the Sun, using the star's own gravity to accelerate itself. Even at this incredible speed, which is about 17 times faster than the Apollo missions, the probe still requires months to complete its solar orbits. And our star is close. It is right here in our own cosmic neighborhood. It is the star our world orbits. It is the source of all the light and warmth that makes life on Earth possible. We see it every single day. It is a constant, familiar presence. And still, it is 150 million kilometers away, a distance so vast that even our most advanced spacecraft take months to cross it. When we then turn our attention to the distances to other stars, even the great chasm separating us from our own Sun begins to seem tiny in comparison. The Sun is our nearest star, and it is 150 million km away. When we contemplate the vastness of space, our familiar units of measurement quickly begin to fail us. Consider the distance from Earth to the Sun, a journey that our fastest probes take months to traverse. Now, imagine a distance 266,000 times greater than that. This is the gulf that separates us from Proxima Centauri, the nearest star to our solar system. Confronted with such scales, astronomers recognized the need for a different kind of yardstick. This wasn't born from a desire to complicate matters or to overwhelm with large figures, but from a simple, practical necessity. On a cosmic canvas, kilometers simply lose their utility. Attempting to map the stars using kilometers would be akin to measuring the expanse between continents in millimeters. While technically feasible, the resulting numbers would become so immense that they would cease to convey any real meaning. They would transform from tangible distances into abstract strings of digits, mathematical concepts detached from any human experience. To bridge this gap in understanding, astronomers conceived of a new unit, the light year. It is essential, however, to clarify a common point of confusion from the outset. Despite the presence of the word year, a light year is not a measurement of time. It is, and has always been, a measure of distance. Specifically, it represents the total distance that a beam of light travels through the vacuum of space in the course of a single Earth year. The reason for basing this cosmic ruler on light is profound. Light holds a special status in our universe. It is the ultimate speedster. Nothing can travel faster than light. This is not merely a technological barrier we have yet to overcome, but rather a fundamental principle woven into the laws of physics. The speed of light is an absolute constant, unchanging, and universal. Whether you are on Earth, on Mars, in a distant galaxy, or at the very edge of the observable cosmos, light consistently moves at the same velocity. That constant speed is approximately 300,000 kilometers per second. It's a figure worth repeating because of its importance. 300,000 kilometers traveled in a single second. This is not a rough guess. It has been measured with incredible accuracy. The precise value is 299,792.458 kilometers per second. But for most purposes, the rounded figure of 300,000 kilometers per second serves perfectly well. The sheer velocity is almost beyond our ability to truly grasp. To offer some perspective, a pulse of light could circle our planet's equator about 7.5 times in the brief moment it takes to snap your fingers. In just 1 second, light could make the round trip from New York to Los Angeles and back again roughly 37 times. It is a speed so extreme that we have no parallel for it in our daily lives. The swiftest object most of us will ever encounter is a commercial airplane, which cruises at around 900 kilometers per hour, or a mere 0.25 kilometers per second. Light moves more than 1 million times faster. Even the fastest car ever engineered, the Thrust SSC, which achieved a speed of about 1,200 kilometers per hour, translates to only 0.33 kilometers per second. Light outpaces it by a factor of about 900,000. When we look to our most advanced creations, like the Parker Solar Probe, we find a machine capable of reaching a peak velocity of 192 kilometers per second. While this is an astonishing speed by human standards, it represents only about 0.064% of the speed of light. Compared to a photon, our fastest spacecraft is moving at a crawl. This incredible speed is why, when you flip a switch in a room, the illumination appears to be instantaneous. The light travels from the bulb to your eyes in approximately 10 billionths of a second, a delay so infinitesimal that it is utterly imperceptible to our senses. As far as our brains are concerned, the light simply appears. Yet, in that fleeting moment, the light did travel. It did take time. We see a more noticeable effect when we look to the heavens. The sunlight that warms your face is not from this exact moment, but from 8 minutes and 20 seconds in the past. That is the duration of light's journey from the sun to the Earth. The sun is so distant that even at 300,000 kilometers per second, its light requires over 8 minutes to span the gap. This leads to a fascinating consequence. If a major event were to occur on the sun right now, if it were to abruptly change color, dim, or even explode, we on Earth would remain oblivious for more than 8 minutes. The event would have already happened, but the light carrying the news of that event would still be in transit. We would continue to see the sun not as it is, but as it was. When you gaze at the moon, you are seeing it as it existed about 1.3 seconds ago. It is a much shorter delay, but a delay nonetheless. During the Apollo missions, this time lag was a tangible part of the conversations between the astronauts on the lunar surface and mission control back on Earth. Every word spoken by an astronaut took 1.3 seconds to travel to Earth, and every reply from Houston took another 1.3 seconds to return to the moon. This introduced a gap of nearly 3 seconds into every single exchange. If you listen to the historical recordings, you can distinctly hear this pause, this slight hesitation, which was the unavoidable consequence of radio signals traveling at the finite speed of light. Light does not travel instantaneously. Its speed, while immense, is finite. This realization stands as one of the most crucial discoveries in the history of physics. Before the latter part of the 1600s, it was widely assumed that light's travel was immediate. After all, when you open your eyes, you see the world instantly. But in 1676, a Danish astronomer named Ole Rømer was making meticulous observations of Jupiter's moons and noticed a curious anomaly. He saw that the timing of the moon's eclipses, as they passed behind Jupiter, seemed to vary depending on Earth's position in its orbit. When Earth was closer to Jupiter, the eclipses occurred earlier than his predictions suggested. When Earth was farther away, they happened later. Rømer correctly deduced that this discrepancy was because light required time to cross these different distances. He estimated that it took light about 22 minutes to traverse the diameter of Earth's orbit. While his calculation was not perfectly accurate, as the precise size of Earth's orbit was not yet known, his work provided the first real proof that light possesses a finite speed. Today, we have measured the speed of light with extraordinary precision using lasers, atomic clocks, and highly sophisticated instruments. We have confirmed that it is a constant, unaffected by your own motion or your location in the universe. What is truly remarkable is that this speed is not just a property of light itself, it is a fundamental characteristic of space-time. So, to find the distance of 1 light-year, we perform a calculation. We take the speed of light, 300,000 kilometers per second, and multiply it by the number of seconds in a year. With 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year, the equation becomes 300,000 times 60, times 60, times 24, times 365. The result is a distance of approximately 9.46 trillion kilometers. The more exact figure is 9,460,730,472,580.8 kilometers, but for ease of use, we typically round it to 9.46 trillion kilometers. This is the immense scale of a single light year. A light year is a unit of distance. It is not a measure of time. It represents the journey that light completes across the vacuum of space in a single year. This distance is 9.46 trillion kilometers. Light is the fastest known entity in our universe. To truly understand this number is to begin to understand our place within the cosmos. It helps us grasp the profound vastness between the stars. It reveals the true and humbling scale of everything. But first, we must consider the number at its very heart. We need to explore what a trillion actually means. For most of us, this number exists without any intuitive sense of its enormous size. We hear large numbers often in our daily lives. We speak of millions, billions, and even trillions. Government budgets are discussed in terms of trillions. We hear about the wealth of billionaires and the populations of millions, yet we rarely pause to feel the immense differences between these quantities. They all register in our minds as simply big numbers. We tend to treat them as if they are roughly equivalent, but they are not. The gulfs that separate them are truly profound. Let's begin with 1 million. A million is simply 1,000 thousands. Imagine saving $1 every single day. You would never miss a day. It would take about 2,740 years to have $1 million. This is a very long time, but it is a period we can still conceive of. We can imagine a timeline stretching back 2,740 years. This journey through time takes us to ancient Greece. It takes us to the early days of the Roman Republic. It was a time when civilizations were already building great cities. They were writing books and creating art. Humanity was already well established. This span of time is comprehensible to the human mind. Now, let's consider a billion. A billion is 1,000 millions. Here, we make a jump of 1,000 times. The scale changes dramatically. Imagine again that you are saving $1, but this time you save it every single second. Not every day, but each second that passes. At this rate, you would need nearly 32 years to save $1 billion. This is more time than it takes for an entire generation to grow up. If you started counting seconds from the moment you were born, you would have to count continuously. You could not stop for sleep. You could not stop to eat. You could take no breaks whatsoever. You would be 32 years old when you finally reached 1 billion. The contrast is what is most important to understand. 1 million seconds passes in about 11.5 days. This is a period we can easily imagine. It is less than 2 weeks. 1 billion seconds, however, is 32 years. The leap from 1 million to 1 billion is simply enormous. Then we arrive at 1 trillion. 1 trillion is 1,000 billions. It is at this stage that numbers begin to disconnect from anything we can relate to. If you were to count to 1 trillion, one number per second without stopping, the task would take you 31,700 years. Let's try to put that amount of time into perspective. This duration is longer than the whole of recorded human history. Civilization's foundation, agriculture, was invented only about 10,000 years ago. Before that time, all humans lived as hunter-gatherers. They moved constantly from place to place. They followed the great herds of animals and the cycles of seasonal plants. Systems of writing appeared in Mesopotamia just 5,000 years ago. The Great Pyramids of Egypt were built around 4,600 years ago. The wheel was likely invented about 5,500 years ago. To count to 1 trillion, You would need to have started your count long before any of these things happened. You would have had to begin when humans still lived in small, nomadic tribal groups. There were no cities then. There were no nations. There was no written language. No agriculture existed. There were no permanent settlements. You would have been counting through the entire span of human civilization. You would have counted through every invention. You would have counted through every discovery. You would have counted through every empire that rose and every empire that fell. You would have counted through every war, every peace, every human triumph, and every tragedy. And you would still be counting today. You would still have thousands of years remaining before you finally reached 1 trillion. Let's make this even more concrete. 31,700 years ago, modern humans were living in the last ice age. Our only tools were crafted from stone. We were hunting woolly mammoths. We hunted giant ground sloths. We had only just begun to spread across the globe. Modern humans had only recently departed from Africa. We were just starting to populate Europe and Asia. There was no language as we know it today. There was no art beyond the most basic cave paintings. There was no technology beyond sharp rocks and wooden spears. That is how far back in time 1 trillion seconds takes us. And a light year is 9.46 trillion kilometers. Each one of those kilometers is a real, physical distance. It is not an abstract concept. It is a length you could walk in about 10 to 12 minutes at a normal pace. There are 9.46 trillion of these individual kilometers in just one light year. That is 9.46 trillion separate, distinct, kilometer-long segments. Each one is the length of a short walk to a local store. So when we say a light year is 9.46 trillion kilometers, we are speaking of a distance that dwarfs anything in our daily experience. You can write this number down. You can perform calculations with it. You can use it in scientific equations. But to grasp it intuitively is nearly impossible. Our brains simply did not evolve to process numbers this large. We evolved to count the people in our tribe. We counted the animals in a herd. We counted the number of days until the seasons changed. We can count to a few hundred. Maybe we can manage a few thousand if we concentrate very hard. But 9.46 trillion is so far beyond our cognitive abilities that it might as well be infinity. The best way to understand a light year may be to build up to it gradually. We can start with distances we can comprehend. We can scale up, step by step. We will take this journey slowly. We will move from the familiar to the unfamiliar. We will watch as distances that seem vast become tiny compared to what comes next. Let's begin with 1 light second. A light second is 300,000 kilometers. That is roughly the distance from the Earth to the Moon and 3/4 of the way back. Think about what this means. Light leaves the Earth. It travels all the way to the Moon, which is 384,000 kilometers away. It bounces back from the lunar surface. It gets about 3/4 of the way back to Earth. All of this happens in 1 second. 1 single second. During the Apollo missions, when astronauts on the Moon talked to Mission Control in Houston, there was a communication delay of about 1.3 seconds each way. The astronauts would say something, and Mission Control would not hear it for 1.3 seconds. This was because the radio signal, traveling at the speed of light, needed that long to make the journey. When Mission Control replied, their response took another 1.3 seconds to reach the Moon. So, every exchange had a delay of nearly 3 seconds built into it. It is a subtle thing when you listen to the recordings, but it is always there. There is this pause, this lag, because of the distance the signals had to travel. And it exists because nothing, not even radio waves, can travel faster than light. 1 light minute is 60 light seconds. This is a distance of 18 million kilometers. The Sun is about 8 light minutes away from the Earth, a distance of about 150 million kilometers. So, 1 light minute is roughly 12% of the distance from the Earth to our Sunday. Imagine, for a moment, that you could stand on the surface of the Sunday. While this is impossible, as the Sun is a sphere of plasma burning at roughly 5,500 degrees Celsius, the thought experiment is revealing. From that vantage point, your view of Earth would not be of the present moment, but of its recent past. You would be seeing our planet as it existed 8 minutes and 20 seconds ago. If Earth were to suddenly vanish, you would remain unaware of the event for that full duration. The catastrophe would occur. but the light carrying the information of that final moment would require over 8 minutes to traverse the vast distance separating our world from its star. This fundamental limit of physics has tangible consequences for space exploration, a detail often overlooked. When NASA directs its rovers across the surface of Mars, a persistent communication delay is an unchangeable reality of the mission. The distance between Earth and Mars is not fixed. It fluctuates as the two planets follow their separate orbits around the Sunday. At their closest alignment, on the same side of the Sun, Mars is approximately 32 million kilometers away, a distance light crosses in about 2 minutes. When they are at their farthest, on opposite sides of the Sun, that gap widens to about 400 million kilometers, which translates to a 22-minute journey for a radio signal. This means that for the Perseverance rover on Mars, every command transmitted from Mission Control on Earth takes anywhere from 2 to 22 minutes to be received. Consequently, any data, from a simple sensor reading to a complex panoramic image, requires the same amount of time to travel back. It is simply not possible to operate a Martian rover in real time, the way one might drive a remotely controlled car. The time lag is far too significant. Instead, the process for NASA engineers becomes one of meticulous, long-range planning. They must carefully study images from previous Martian days, chart a safe and productive course, and then compile a precise sequence of commands. Once this sequence is sent, they can only wait. Should an unexpected issue arise, such as the rover becoming lodged against a rock or encountering an unforeseen obstacle, an immediate response is impossible. Mission Control must first wait for the signal carrying news of the problem to arrive, a delay of up to 22 minutes. Then, engineers must analyze the situation, devise a solution, write a new set of commands, and transmit them. Finally, they must wait another 2 to 22 minutes for those instructions to reach the rover. A problem that could be solved in seconds with a terrestrial remote-controlled vehicle might take an hour or even longer to address on Mars. Expanding our scale, 1 light hour is equivalent to 60 light minutes, a distance of about 1,080,000,000 kilometers. It is a scale of distance that begins to challenge comprehension. The planet Saturn, when it is nearest to Earth, is approximately 1.2 light hours away. As one of the most distant celestial bodies visible to the naked eye, this beautiful, ringed world has captivated observers since antiquity, and yet it lies over a light hour from us. When the Cassini spacecraft orbited Saturn between 2004 and 2017, it captured breathtakingly detailed photographs of the planet and its moons. Each of these images, however, was subject to a delay of more than an hour between the moment of its capture and its reception back on Earth. The probe would take a picture, convert that image into digital data, and transmit it as a radio signal, moving at light speed. Over an hour later, that signal would finally reach the scientists waiting for it. This inherent delay meant that Cassini could never be piloted directly. Engineers and scientists were unable to see what the spacecraft was seeing and make instantaneous adjustments to its trajectory, as one might steer a car or fly a drone. Instead, entire operational sequences had to be programmed days or even weeks ahead of time. These command lists were then uploaded to the spacecraft, with the team trusting Cassini to execute them flawlessly. The probe also had to be intelligent enough to handle potential problems on its own. If an anomaly occurred, Cassini was designed to recognize the issue and enter a protective safe mode autonomously. By the time a distress signal reached Earth and new instructions were sent back, more than 2 hours would have elapsed, a period in which the situation could have changed dramatically. A light day measures 24 light hours, or roughly 25,900,000,000 kilometers. At these distances, even our most rapid spacecraft seem incredibly slow. Consider Voyager 1, which launched in 1977 and currently holds the record as the most distant human-made object from Earth. As of 2025, it is about 24 light hours away. For nearly half a century, it has been traveling at approximately 17 kilometers per second, which is about 61,200 kilometers per hour. By any terrestrial standard, this speed is immense. You could cross the entire United States in about 2 minutes. And yet, after nearly 5 decades of continuous travel through the vacuum of space with nothing to impede its progress, Voyager has still not traveled the distance light covers in a single day. This distance is also roughly the boundary of the heliopause, the theoretical edge where the sun's influence wanes and interstellar space truly begins. The heliopause is where the solar wind, a constant stream of charged particles flowing outward from the sun, finally slows and mixes with the interstellar medium, the tenuous gas that permeates the space between stars. Voyager 1 passed this monumental threshold in 2012, becoming the first human artifact to enter interstellar space. It was a historic achievement in human exploration, but in cosmic terms, the probe is still right in our immediate neighborhood, less than a light day from home. 1 light week is 7 light days, a distance of about 181 billion kilometers. We are now in a region where no human object has ever ventured, and none will for many decades, or perhaps centuries. This is deep space, far beyond the orbits of the planets and anything we have directly explored. From this vantage point, the sun would no longer be the overwhelming source of light and heat we experience on Earth. It would appear simply as a very bright star, brighter than any other, certainly, but still just a single point of light against the darkness. If you were floating in space 1 light week from our solar system, you would see our sun as a brilliant star, but you would also see thousands of other stars scattered across the black tapestry of the sky. It is here you might truly appreciate that our sun is just one star among countless others. A light month is approximately 30 light days, or about 778 billion kilometers. At this immense distance, looking back at the sun even through a telescope would reveal it as just another star, not significantly more brilliant than many others. The entire solar system, with all its planets, moons, asteroids, and comets, would be nearly invisible. A powerful telescope might resolve Jupiter as a faint speck of light, but the inner planets would be completely lost in the sun's glare. Everything we consider our solar system, all the planets we have studied and the worlds we know, would be compressed into a minuscule region surrounding a very ordinary star. And 1 light year is equivalent to 365 light days. It is 12 light months, or 52 light weeks. It represents 8,760 light hours and 525,600 light minutes. A single year contains 31,536,000 light seconds, a number that reveals how quickly these measurements escalate. The journey began with 1 light second, a distance already immense by any human measure, roughly equivalent to traveling from the Earth to the Moon and most of the way back. From there, the units have been multiplied by progressively larger values, 60 seconds in a minute, 60 minutes in an hour, followed by the days, weeks, and months that compose a year. Only after all this multiplication do we arrive at the definition of a single light year, which is 9.46 trillion kilometers. This represents the total distance that light covers in 1 year, an uninterrupted journey at 300,000 kilometers per second for 365 consecutive days. This particular unit has become fundamental for astronomers when charting the cosmos, as the gaps between stars are measured in light years. Any smaller increment would be impractical when contemplating such vast cosmic scales. The reason astronomers rely on light years is straightforward. All other alternatives are less effective. Consider the awkwardness of using kilometers for interstellar distances. The nearest star, Proxima Centauri, is approximately 40,140 billion kilometers from us. Such a figure is difficult to remember and offers little intuitive grasp of the separation. In contrast, stating that Proxima Centauri is 4.24 light-years away provides a much cleaner and more useful piece of information. It allows for immediate comparison. If one star is 4 light-years away and another is 40, it is instantly clear that the second is 10 times more distant. Light-years also create a meaningful link between distance and time. When we observe a star that is 4 light-years away, we are seeing the light that departed from it 4 years in the past. In essence, we are looking back through time. This connection is of critical importance in the study of the universe. The speed of light is not merely fast, it serves as the ultimate velocity limit in the cosmos. Nothing is capable of moving faster. This is not a technological barrier that future engineering or more advanced rockets might someday overcome. Instead, it is a fundamental principle of physics woven into the very fabric of space-time. The speed of light is more than a velocity. It is a cosmic constant that governs the relationship between space, time, energy, and matter. In his 1905 theory of special relativity, Einstein demonstrated that peculiar phenomena occur as an object approaches this cosmic speed limit. These are not simply theoretical ideas, but observable realities confirmed by innumerable experiments conducted over the last century. For an object in motion, time slows down relative to observers who are stationary, an effect known as time dilation that has been directly measured. The object's inertia also increases, making it progressively more difficult to accelerate. As its velocity nears the speed of light, the energy needed to push it faster grows infinitely. To actually attain the speed of light would demand an infinite quantity of energy, which is an impossibility as the universe does not contain it. Consequently, no object possessing mass can ever reach the speed of light. An analogy helps to clarify why this is the case. In our daily lives, if you are on a train traveling at 50 kilometers per hour and throw a ball forward at 20 kilometers per hour relative to the train, an observer on the ground would see the ball moving at 70 kilometers per hour. The speeds simply add together. This seems perfectly logical and functions well at ordinary velocities. However, Einstein revealed that this simple addition fails when dealing with speeds approaching that of light. If you were on a spacecraft moving at half the speed of light and turned on a flashlight, you might expect the light beam to travel at 1.5 times light speed from the viewpoint of a stationary observer, but this is not what happens. The light moves at precisely the speed of light, 300,000 kilometers per second, for both the person on the spacecraft and the person watching from the outside. This seems paradoxical. The resolution lies in the fact that space and time themselves adjust to ensure the speed of light remains constant for everyone. When you are moving at very high speeds, time literally passes more slowly for you from the perspective of someone at rest. Furthermore, distances in your direction of motion actually contract. These are not optical illusions or errors in measurement. They are genuine physical effects. Time and space are not absolute quantities, but are relative, changing based on one's motion. The only constant, the only thing that remains the same for every observer, is the speed of light. This principle has been experimentally verified on countless occasions. In particle accelerators, particles are propelled to velocities extremely close to the speed of light. Scientists can measure their lifespan before they decay and have found that particles moving at 99.9% of light speed exist much longer than identical particles at rest. For them, time is genuinely moving at a slower rate. This is not a theory but a measured fact. The atomic clocks aboard GPS satellites orbiting the Earth also provide proof. These satellites move quickly enough and are far enough from our planet's gravity that time dilation becomes a measurable factor. Their clocks run at a slightly different rate than identical clocks on the ground. If the GPS system did not correct for this effect, its navigation would become inaccurate by several kilometers in just a matter of hours. The reliability of GPS is a daily confirmation that time dilation is real. Another example comes from cosmic rays, which are high-energy particles from space. When they strike the upper atmosphere, they create particles called muons. Muons are unstable and decay very rapidly, with a half-life of about 2 microseconds. At that rate, even when traveling near the speed of light, muons created high in the atmosphere should not survive long enough to reach the ground. And yet, muons are detected at ground level consistently. The reason is that from our stationary perspective, the muons' extreme speed causes time dilation to extend their lifespan. What is a mere 2 microseconds in the muons' frame of reference becomes a much longer duration in ours, allowing them to complete their journey. Only particles without mass, such as photons, the particles of light, can travel at the speed of light. Since photons have no rest mass, they do not require infinite energy to reach this velocity. In truth, photons must always travel at light speed. They are incapable of slowing down or speeding up. From the instant of their creation to the moment of their absorption, they travel at exactly the speed of light, no more and no less. This is their fundamental nature. All of this has profound consequences for the dream of space travel, extending far beyond mere engineering hurdles. Even if humanity were to develop perfect propulsion systems with access to limitless energy, and even if we could solve every conceivable technical problem, we would still be unable to travel faster than light. Even if a spacecraft could be accelerated to nearly the speed of light, the most optimistic scenario imaginable, the journey to Proxima Centauri would still require a minimum of 4.24 years, and that is only to reach the very nearest star. The vast majority of cosmic destinations are immensely farther away. Science fiction often envisions methods for circumventing this fundamental constraint. Concepts include warp drives, which would bend space-time around a vessel, enabling it to arrive at a destination faster than light without locally breaking that cosmic speed limit. Other ideas involve wormholes, which could form shortcuts through the fabric of space-time to connect distant locations, or hyperspace, a theoretical alternate dimension where different physical laws might permit faster than light travel. While these are creative notions, some, like the warp drive, have a foundation in theoretical physics. The Alcubierre drive, first proposed in 1994, is a theoretical model consistent with Einstein's field equations that would allow for faster-than-light travel by contracting space in front of a ship while expanding it behind. But the concept is fraught with problems. The primary obstacle is its requirement for exotic matter, a substance with negative energy density, which has never been observed and is not known to exist. Some physicists believe it may be impossible on a fundamental level. Even if such matter were to exist, the amount needed would be astronomical, possibly greater than the total mass energy of the entire observable universe. There are also profound issues with causality. The ability to travel faster than light would also theoretically permit travel into the past, raising the spectre of causality paradoxes. Wormholes, should they exist, would likely be incredibly unstable, collapsing before anything could traverse them. The energy required to keep a wormhole open long enough for passage might exceed all the energy available in the universe. And here, too, causality problems arise. If wormholes allow for faster-than-light travel, they would also enable journeys to the past, with all the associated logical contradictions. The notion of hyperspace is purely speculative, with no basis in our current understanding of physics. It remains a compelling storytelling device, but lacks any connection to real physics or mathematics. There is simply no evidence that such a thing exists, or even could exist. Based on over a century of meticulous experiments and observations, everything we know suggests the speed of light is an absolute barrier. It is not a technological challenge to be overcome, but rather a fundamental law of nature. When we speak of stars that are hundreds or thousands of light years away, we are discussing distances that may be fundamentally beyond our reach with any technology that abides by the laws of physics as we currently understand them. The light year, in this sense, measures more than just distance. It also measures a boundary, a limit beyond which the ordinary rules of cause and effect appear to break down. To truly grasp these scales, it is helpful to consider Proxima Centauri, our closest stellar neighbor. Examining this star gives us a practical sense of what it means when we say that even the nearest stars are almost impossibly distant. Proxima Centauri is a small red dwarf star within the Alpha Centauri system, which is actually a triple star system. Two of its members, Alpha Centauri A and B, are sun-like stars that orbit one another. They are comparable in size and brightness to our own sun, and they complete a slow gravitational dance around their common center of mass every 79.9 years, a celestial ballet that has continued for billions of years. If one could view them up close, Alpha Centauri A and B would appear as two suns circling each other against the deep black of space. Proxima Centauri is considerably smaller, with about 1/8 the mass of the Sun and 1/7 its diameter. It is so small and faint that it cannot be seen with the naked eye. An intriguing detail is that despite being our nearest stellar neighbor, a telescope is required to spot it. Red dwarfs like Proxima Centauri are the most prevalent type of star in the galaxy, comprising about 70% of all stars. However, they are all so dim that not a single one is visible to the unaided eye. This leads to a remarkable realization. Every star you can see in the night sky is either larger and brighter than our Sun, or it is not a star at all, but a planet in our solar system. The distance to Proxima Centauri is 4.24 light years, or about 40 trillion, 140 billion kilometers. That is the number 40 followed by 12 zeros. To put this in perspective, if you were to travel at the speed of the fastest spacecraft ever built by humans, the Parker Solar Probe, at 192 kilometers per second, the trip would take approximately 6,800 years. This duration is longer than all of recorded human history. The invention of writing occurred about 5,000 years ago. One could have begun a journey when humans first learned to write, traveled non-stop at the highest speed any human-made object has ever achieved, and would still be traveling today, with thousands of years remaining before reaching the destination. Proposals for much faster spacecraft do exist. The Breakthrough Starshot Initiative, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, suggests using powerful ground-based lasers to accelerate tiny spacecraft to about 20% of light speed. The concept is elegant and, at least in principle, scientifically sound. The idea is to build a spacecraft that is essentially a computer chip with a camera weighing perhaps a gram attached to an ultra-thin light sail made of a reflective material only a few atoms thick. Then, massive arrays of lasers on Earth would be aimed at it. The pressure from the laser light would push on the sail, and because the craft is so incredibly light, it could be accelerated to tremendous speeds. At 20% of light speed, which is about 60,000 kilometers per second, a probe could reach Proxima Centauri in roughly 20 years. If you add another 4 years for signals to travel back to Earth at the speed of light, it would be possible to receive data from Proxima Centauri within 24 years of launch. That timeframe is within a human lifetime, which is an exciting prospect. A mission could be launched in one's youth, with the results potentially seen before one's death. But the engineering challenges are enormous, perhaps insurmountable with current or near-future technology. First, the plan requires lasers of incredible power. The proposal calls for a laser array with a total output of about 100 gigawatts. This is roughly the energy produced by 100 nuclear power plants, all focused into a laser beam a few kilometers wide. This beam would then need to track the tiny spacecraft with perfect precision as it accelerates, keeping the light focused exactly on the sail. The sail must remain perfectly centered within the powerful laser beam. Any deviation would cause it to drift away from the propulsive force, halting its acceleration and leaving it to coast at its last achieved velocity. A second major obstacle is ensuring the probe's survival through the interstellar medium. Traveling at 20% of light speed means moving at an incredible 60,000 kilometers per second, a velocity at which impacts with even the smallest particles become catastrophic. A collision with a speck of dust, smaller than a grain of sand, would release the energy of a large bomb. While shielding could offer protection, it introduces a critical dilemma: mass. Weight is the ultimate adversary when propulsion relies on the faint pressure of light, as every added gram requires substantially more power for acceleration, making the engineering equation increasingly difficult. A third challenge involves establishing communication across more than 4 light-years of space. The minuscule probe would need a transmitter powerful enough to send its findings back to Earth from a distance of 4.24 light-years. Over such an expanse, any signal naturally weakens and disperses, so the power needed for a detectable transmission is considerable, a capability that must be engineered into a craft the size of a computer chip. The task is akin to shouting across an ocean and expecting to be heard with clarity on the opposite shore. The fourth hurdle is one of extreme navigational precision, requiring the probe to fly past the Proxima Centauri system at the perfect distance and angle to gather useful data. At 1/5 the speed of light, the craft moves so swiftly that it would cross the orbit of Mars in only 40 minutes and traverse the entire diameter of our solar system out to Neptune in about 6 hours. This allows for only a single attempt. There can be no slowing down and no course corrections once the probe is at speed, because deceleration would demand the same immense energy as the initial acceleration, an amount of power a gram-scale spacecraft simply cannot carry. The probe would therefore streak past Proxima Centauri at 60,000 kilometers per second, with a brief window of just a few hours, or perhaps a few days, to capture its precious measurements and images. Afterward, it would continue on into the void, drifting through interstellar space, never to be seen again. So, while the breakthrough starshot concept is a compelling idea rooted in real physics, it remains almost entirely theoretical. The technology for it does not yet exist, and it faces formidable obstacles that may prove to be insurmountable. Even in an ideal scenario where we could build and launch such a craft tomorrow, it would take at least 20 years to reach Proxima Centauri, followed by another 4 years for any data to return to Earth. That represents a 24-year round trip for information assuming a perfect mission, which has never been a reliable expectation in the history of space exploration, and all this effort would be just to visit our nearest stellar neighbor. Using the technology we can actually build today with our current rockets, materials, and computer systems, a journey to Proxima Centauri would take not decades, but millennia. It would require the construction of massive, multi-generational world ships, vessels capable of sustaining human crews for thousands of years. The people who would finally arrive at the destination would be the distant descendants of those who departed, separated by hundreds of generations, having lived their entire lives inside a traveling world, journeying to a place they knew only from stories passed down through the ages. When you look up at the night sky, you are seeing stars at different distances, and you are therefore seeing them as they were in the past. This is one of the most profound implications of the light year. Distance and time are inseparable. You cannot observe where something is without also observing when it was. Light travels at a finite, though incredibly fast, speed. It is not instantaneous. As light leaves a star and crosses the void toward Earth, that journey takes time. During that passage, the star itself might have changed. Its brightness could have shifted, its color could have altered, or it might have exploded. By the time its light reaches your eyes, the star you perceive could be completely different from how it exists in the present moment, or it might not exist at all. Sirius, the brightest star in our sky, is 8.6 light-years away. When you look at Sirius tonight, you are seeing light that left that star 8.6 years ago. You are seeing it as it was when you were 8.6 years younger. If you are 20 years old, you are seeing Sirius as it appeared when you were about 11, likely in middle school. If you are 40, you are seeing it as it was in your early 30s. The Sirius you see is an image from the past, not the star as it is right now. Of course, Sirius is a stable main sequence star, so it does not change noticeably over a few years or even decades. In 8.6 years, it barely ages from a human perspective, as stars evolve on timescales of millions or billions of years. But the principle is what is truly significant here. You are not seeing Sirius as it is, but as it was. Every time you look at a star, you are looking back in time. Vega offers another example, a bright star about 25 light-years away. If you are 25 years old and you look at Vega, you are seeing light that departed that star in the year you were born. When that light began its journey, you did not yet exist. Your parents might have looked up at that same star, seeing light that had left Vega 25 years before that, 50 years in the past. The Vega you see tonight is a younger version of the star, showing you what it looked like a quarter century ago, not as it is now. Then there is Betelgeuse, the red supergiant in the constellation of Orion, which is about 550 light-years away. It is one of the most famous stars in the night sky, easily identified as the bright, reddish point of light on Orion's shoulder. The light you see from Betelgeuse tonight started its journey to Earth around the year 1474 during the Italian Renaissance. This was before Columbus sailed to the Americas, when Leonardo da Vinci was 22 years old and Michelangelo was about to be born. In 1474, the Byzantine Empire had fallen to the Ottoman Turks 21 years earlier, and the printing press had been invented only about 20 years before. Most of Europe was still emerging from the Middle Ages. The modern world as we know it had not yet taken shape. It was from that distant past that the light of Betelgeuse you see tonight began its long voyage. The light from Betelgeuse that enters your eye this evening has been on a voyage for over 500 years, traversing the immense darkness between that distant star and our planet. Betelgeuse presents a particularly compelling subject, as it is a colossal star approaching the conclusion of its existence. Stars of this magnitude do not live as long as smaller ones like our Sun. Their fuel is consumed at a much more rapid pace. At some point in the astronomically near future, perhaps within the next 100,000 years, Betelgeuse is destined to erupt as a supernova. When this happens, its brightness in our sky will momentarily rival that of the full moon, making it visible even in daylight. It promises to be an extraordinary sight, one of the most profound celestial events witnessed from Earth in all of human history. Yet, an intriguing possibility remains. The star may have already detonated. This explosion could have occurred centuries in the past, maybe in the year 1600, or 1700, or even 1800. We would have no knowledge of it yet, as there is no way for us to know. The illumination from such an event would still be making its way toward us, moving at the speed of light on its 550-year trip. Consequently, if Betelgeuse did explode in the year 1700, we would not witness the event until around the year 2250. The star could be gone at this very moment, annihilated in a cataclysmic supernova, yet we would continue to see it shining serenely in the night sky for centuries. We would remain entirely unaware that we are observing a ghost, an afterimage of an object that has ceased to exist. Polaris, which we know as the North Star, is situated approximately 445 light-years from us. When the light we see from it tonight commenced its journey, the first lasting English settlements in North America had not yet been founded. The establishment of Jamestown was still 12 years away, and the Pilgrims would not land at Plymouth Rock for another 26 years. At that time, William Shakespeare had only just started his playwriting career. He had penned some of his earlier plays, but had not yet created Hamlet, Macbeth, King Lear, or the majority of his most renowned works. The United States as a nation was still 180 years from its inception. The world was a profoundly different place when that light from Polaris began its long voyage, and tonight, that very ancient light is captured by your eye, connecting you across space and time through photons that have traveled for 4.5 centuries. Within a radius of about 20 light-years from Earth, astronomers have identified roughly 130 known star systems. Some of these are solitary stars, similar to our own Sunday. Others are binary systems, featuring 2 stars in orbit around one another, or even triple star systems like the one found at Alpha Centauri. Gaining an understanding of our stellar vicinity helps us grasp both the sheer scale of the distances involved and the diversity of stars populating our cosmic neighborhood. Barnard's star, located about 6 light-years away, is the second closest star system to Earth, after Alpha Centauri. It is a red dwarf, significantly smaller and fainter than the Sunday. What makes Barnard's star especially noteworthy is its relatively rapid movement toward us by celestial measures. It exhibits the largest proper motion of any star known, which means that from our perspective on Earth, it appears to move across the sky more quickly than any other star. Over spans of decades and centuries, we can actually observe the position of Barnard's star shifting in relation to the stars around it. In approximately 10,000 years, it will be nearer to Earth than Proxima Centauri is today, making it our new closest stellar neighbor. Even at its point of nearest approach, however, it will remain almost 4 light-years distant. The gaps between stars are so immense that even when they are moving closer, it requires thousands or even tens of thousands of years for this motion to create a significant change in the distance separating them. Wolf 359, at a distance of about 9 light-years, is one of the fastest stars in relation to the Sun, moving at a speed of about 119 kilometers s. This is considered fast by stellar criteria. The majority of stars in our galactic region travel at speeds of just a few tens of kilometers s relative to their neighbors. Wolf 359 is moving considerably faster, and yet, even at this velocity, it is only traveling at about 0.04% of the speed of light. Stars are in motion, but their movement is slow when compared to the vast distances that lie between them. Even the quickest nearby star would need tens of thousands of years to cover the distance of a single light-year. Sirius, 8.6 light-years away, is in fact a binary system composed of 2 stars orbiting each other. The first, Sirius A, is a brilliant white main sequence star with about twice the mass of the Sunday. It holds the title of the brightest star in our night sky, a status due partly to its relative proximity and partly to its high intrinsic luminosity. Its companion, Sirius B, is entirely different. It is a white dwarf, the compact remnant of a star that used up its nuclear fuel and subsequently collapsed. White dwarfs are remarkable objects. They are typically the size of Earth but contain the mass of a star. Sirius B, for instance, holds approximately the mass of our Sun, but this mass is compressed into a sphere roughly the size of our own planet. This results in an object of incredible density. A single teaspoon of matter from Sirius B would weigh around 5 tons on Earth. These 2 stars circle each other once every 50 years, bound by gravity, each tracing an elliptical orbit around their shared center of mass. The Milky Way itself is a spiral galaxy that contains an estimated 100 billion to 400 billion stars. The range is so wide because counting the stars in our own galaxy is a remarkably challenging task. We are situated inside it, which is like trying to count the trees in a forest while standing deep within it. Our view is obstructed in many directions by cosmic dust. Faint stars are difficult to spot. Moreover, the galaxy is so enormous that we cannot observe all of it at once from our vantage point. Nevertheless, the best approximations place the number somewhere between 100 billion and 400 billion, with the most probable count being in the vicinity of 200 to 300 billion. Our Sun is merely one of these countless stars, a common yellow dwarf of average size and brightness. From a galactic standpoint, there is nothing particularly special about our Sunday. It is not the largest, the most luminous, the hottest, or the coolest. It is simply a typical star among hundreds of billions of others. Its location is in one of the spiral arms, about 26,000 light-years from the galactic center. Consider that distance, 26,000 light-years. The light we perceive from the heart of our galaxy, assuming we could see past all the intervening dust, departed from the galactic center 26,000 years ago. When those photons started their journey, humans were still living as hunter-gatherers during the Stone Age. The invention of agriculture had not yet occurred. There were no permanent settlements, no cities, and no civilization as we currently define it. People existed in small, nomadic groups, tracking herds of animals, foraging for wild plants, and employing simple tools made of stone. The invention of writing was still 21,000 years in the future. The whole of what we call human civilization, from the first farms and cities to the invention of writing, through all the ancient empires and into our modern world, has taken place entirely within the time that light from the galactic center has been traveling to reach us. That ancient light, which began its immense voyage when our ancestors were still primitive hunter-gatherers, is only now arriving at Earth. The Milky Way galaxy itself spans a distance of roughly 100,000 light-years from one edge of its spiral arms to the other. If it were possible to travel at the speed of light, a feat forbidden by physics, such a journey across the galaxy would last for 100,000 years. To put that into perspective, our own species, Homo sapiens *, has existed for about 300,000 years. This means that if you had embarked on that light-speed journey at the very moment the first modern humans emerged in Africa and travelled for all that time, you would only be about 1/3 of the way across our home galaxy today. Our Sun moves through the galaxy at a considerable velocity, orbiting the galactic center at approximately 230 kilometers per second. While that speed seems immense, fast enough to cross the entire United States in about 3 minutes, or to circle the whole of Earth in just under 3 minutes, the scales of the galaxy render it almost trivial. Even at this incredible pace, the Sun requires between 225 million and 250 million years to complete a single great orbit. The last time our solar system occupied this particular region of space, the very first dinosaurs were just beginning to evolve on Earth, around 230 million years ago. In the vast expanse of time since then, the dinosaurs arose, dominated the planet for over 160 million years, and then vanished 66 million years ago. Subsequently, mammals rose to prominence, and eventually, humans appeared, and only now has the Sun finally returned to approximately the same cosmic position it held at the dawn of the dinosaurs. One of the most profound astronomical shifts in recent decades has been the discovery of exoplanets, which are worlds that orbit stars other than our Sunday. Until the year 1992, humanity was aware of only a single planetary system in the entire universe, our own solar system, with its 8 familiar planets circling the Sunday. We had long suspected that other stars might host their own planets, but we possessed no concrete evidence to support this idea. That all changed in 1992, when astronomers successfully detected the first planets around another star, which happened to be a pulsar. Then, in 1995, a major milestone was reached with the discovery of the first exoplanet found orbiting a normal, sun-like star. From that point forward, the rate of these discoveries has accelerated dramatically. As of 2024, the official catalogue of confirmed exoplanets has grown to well over 5,000, and there are thousands of additional candidates that are currently awaiting verification. A particularly compelling example is the TRAPPIST-1 system, located about 40 light-years from Earth. This system features 7 planets, all of which are similar in size to our own world, orbiting a small, cool red dwarf star. What makes this system especially intriguing is that 3 of these planets lie within the star's habitable zone. This is the specific orbital region where surface temperatures might be suitable enough to permit the existence of liquid water. The 2017 announcement of this discovery was revolutionary for several important reasons. It demonstrated that small red dwarf stars are fully capable of hosting multiple rocky worlds. Considering that red dwarfs are the most abundant type of star in our galaxy, constituting around 70% of the entire stellar population, this finding strongly suggests that rocky planets could be incredibly widespread throughout the cosmos. The architecture of the TRAPPIST-1 system is also fascinating, as its planets are clustered together in remarkably tight orbits. All 7 of these worlds circle their star at a distance closer than Mercury orbits our Sunday. Yet, because their parent star is so dim and cool, 3 of them receive an amount of energy that is comparable to what Earth gets from the Sunday. An observer standing on the surface of one of these planets would be able to witness the other worlds in the sky, some of them appearing even larger than our own moon does from Earth. The planets are situated so near to one another that travel between them would likely be significantly less difficult than it is between the planets in our own solar system. When we observe the TRAPPIST-1 system with our telescopes, we are seeing it not as it is at this moment, but as it was 40 years ago, back in the year 1985. If an intelligent civilization happens to exist on one of those planets and had developed radio technology, any signals they broadcast would require a full 40 years to cross the immense distance to us. This means that a message they transmitted in 1985 would only just be arriving at Earth today. And if we were to detect such a signal now and immediately transmit a reply, our message would take another 40 years to reach them. They would not receive our response until the year 2065. A single, simple exchange of information would therefore require an 80-year round trip. One could pose a question and pass away from old age long before ever receiving an answer. This forces us to consider what communication truly means when distances are measured in light years. It is one of the most sobering and difficult realities imposed by the sheer scale of space. The implications are profound for any future in which humanity might attempt to establish settlements in other star systems or make contact with other intelligent civilizations. Radio waves, being a form of electromagnetic radiation just like visible light, travel at the speed of light. They propagate outward from their source at 300,000 kilometers per second. But even at this ultimate cosmic speed limit, the fastest velocity possible in our universe, any communication across light years inevitably takes years to complete. Our most distant robotic probe, Voyager 1, provides a tangible, real-world example of this delay. It is currently about 24 light-hours away from Earth. This distance translates directly into a one-way communication lag of approximately 24 hours. When mission controllers on Earth send a command to the Voyager spacecraft, that radio signal must travel at light speed for 24 hours just to cover the 25 billion kilometers to reach the probe. Any scientific data or status updates that Voyager sends back in return require another 24 hours to complete the journey to Earth. This creates a total delay of roughly 48 hours for any two-way interaction. The practical consequence of this immense time delay is that the spacecraft must be engineered to operate with a high degree of autonomy. If a critical system were to fail, or some unexpected anomaly were to arise, Voyager has to be capable of managing the situation entirely on its own. By the time engineers on Earth even become aware that there is a problem and can transmit new instructions to correct it, 2 entire days will have already passed. In that considerable span of time, the circumstances aboard the distant spacecraft could have altered completely. A similar challenge was faced by the New Horizons mission team during the spacecraft's historic flyby of Pluto in July 2015. At the moment of its closest approach, the probe was around 4.5 light-hours away from us. All of the valuable scientific data gathered during those few critical hours in the vicinity of Pluto had to be carefully saved on the probe's internal memory banks. That precious information was then transmitted back to Earth very slowly over the course of the subsequent months. Every single command for the intricate flyby sequence had to be programmed and uploaded to the spacecraft weeks or even months beforehand. The mission team had no ability to react in real time to what New Horizons was observing as it happened. They were required to meticulously plan every last detail, foresee all possible scenarios, and place their complete trust in the spacecraft's ability to execute its complex mission independently. Now, with all this in mind, try to imagine the challenge of maintaining even basic communication with a human outpost on a planet that might be orbiting Proxima Centauri, our nearest stellar neighbor, just 4.2 light-years away. Imagine sending a simple message out into the void, perhaps asking about the well-being of distant colonists or the progress of their crops. That transmission, moving at the fastest speed possible, would still need 4.24 years to cross the interstellar gulf. It would be 4 years, 2 months, and roughly 20 days before your question even arrived. Should they reply the moment they receive it, their answer would embark on an identical 4.24-year journey back to you. The result is a delay of more than 8 years for a single back-and-forth exchange. You might inquire about their most recent harvest only to receive a reply concerning crops that were consumed 4 years prior. A question about a person's health could be met with news of their passing, an event that occurred years ago. Any offer of assistance or advice would be rendered obsolete by the time it reached its destination, as the circumstances would have invariably changed. The kind of instantaneous, real-time conversation that forms the bedrock of our society is fundamentally impossible over these scales. Discussions would unfold at a pace that tests the limits of patience. Debates could easily stretch across decades. A diplomatic negotiation between a settlement on Proxima and Earth might take a century or longer to conclude, with each side forced to weigh their words with immense care, knowing years would pass before a response was heard, and years more before their own reply could be delivered. This reality has profound consequences for society and governance that extend far beyond mere inconvenience. A colony situated 4 light-years from Earth could not be governed from home in any practical way. Any laws or directives dispatched from Earth would be years out of date upon arrival. The entire political landscape on Earth could shift dramatically in the time between a message being sent and its reception. By the time a colony receives its orders, those instructions might have been nullified by new administrations or policies. This necessitates that the colony be autonomous, with the authority to make its own decisions on everything from managing resources and resolving conflicts to handling emergencies. Waiting years for guidance or approval on every matter would be an unworkable model. Over time, the colony and Earth would inevitably diverge culturally, each developing unique customs, lifestyles, and solutions to their distinct challenges. They would remain linked by messages from the past, like letters from a bygone era, but they would lack the immediate, continuous connection that binds societies together. After several generations, they might become so different as to be almost unrecognizable to one another. They would share a common point of origin and a mutual history up to the moment of separation. From that point on, however, their paths would fork, leading them to evolve independently, much like species isolated on different islands. For stars at greater distances, the problem becomes exponentially more severe. A settlement 10 light-years away would face a 20-year round-trip communication delay. Messages sent to your children living there would arrive when they are adults, perhaps with families of their own. Their replies would come back when your own grandchildren are grown and you are elderly or perhaps no longer alive. You would be exchanging letters across the decades, like voices from entirely different historical periods. While you could share news and maintain a connection in an abstract sense, a relationship in the conventional meaning of the term would be impossible. A civilization 100 light-years away would contend with a 200-year communication lag. You could send a message, and neither you, nor your children, nor your grandchildren, nor even your great-grandchildren would be alive to see the response. Only your distant descendants, perhaps your great-great-great-grandchildren living in a world you could scarcely comprehend, might receive a reply from that far-flung world. The conversation would be one that spans generations, with each successive generation sending messages to strangers they could never meet. People separated not only by an immense gulf of space, but also by an impassable chasm of time, receiving communications from individuals long since deceased. An extraordinary phenomenon occurs if you could travel at velocities approaching the speed of light. This is the principle of Einstein's time dilation. a concept that has been validated by innumerable experiments. It is not a speculative theory, but an observed reality, as firmly established as the principles of gravity or electromagnetism. As your speed nears that of light, time for you slows down relative to observers who are stationary. The closer you get to light speed, the more pronounced this effect becomes. This is not merely a matter of clocks running slower. It is time itself that is altered. Your own biological processes, your heartbeat, your thoughts, your aging, all proceed at a slower rate from the perspective of someone not moving with you. Yet from your own vantage point inside your spacecraft, everything would seem perfectly normal. For you, time would pass as it always does. It is the rest of the universe that appears to be moving at an accelerated pace. Consider a hypothetical spacecraft capable of attaining 99.9% of the speed of light. While not quite light speed, it is incredibly close. You board this vessel for a journey to a star 10 light-years away and then return. From the perspective of Earth, this round trip takes approximately 20 years, 10.1 years for the outbound leg at 99.9% light speed, and another 10.1 years to come back. Anyone observing from Earth would witness your spacecraft complete its voyage in about 2 decades. However, due to time dilation, you would have aged significantly less. At 99.9% of light speed, time for you passes about 22 times more slowly than for people on Earth. Consequently, while 20 years elapsed back home, you would have experienced only about 11 months. You would step off your ship having aged less than a year, while everyone you once knew had aged 20 years. A younger sibling could now be older than you. Any children you had might now be adults who are older than you are. You have effectively journeyed into their future. If you were to travel even faster, at 99.99% of light speed, you could venture to a star 100 light-years away and return. From Earth's perspective, this expedition would last more than 200 years. But for you, because of the extreme time dilation at this velocity, the entire journey might only consume a few years of your life. You would live through a few years of travel, but upon your return to Earth, over 2 centuries would have passed. Every person you had ever known would be long gone. The world would be an utterly transformed place. Political structures would have risen and fallen. Technologies would have advanced beyond recognition. Languages themselves may have evolved. You would arrive in a future Earth that would feel as alien to you as if you had been transported through time. If we pull our focus back to the largest possible scale, we encounter the observable universe. This is the region of space from which light has had enough time to reach us since the Big Bang. The universe is approximately 13.8 billion years old, and light has been making its journey toward us for that entire duration. The observable universe is considerably larger than its 13.8 billion year age might imply, a direct consequence of the fact that space has been expanding while ancient light journeyed toward us. This results in a visible cosmos that stretches about 46.5 billion light-years in radius, making its total diameter roughly 93 billion light-years. This represents the farthest distance to the edge of what we could ever hope to see. Beyond this immense boundary, the fabric of space has been stretching so quickly that light from those remote areas has not yet reached our vantage point, and it never will. We are surrounded by a cosmic horizon, a fundamental limit defined not by the power of our telescopes, but by the finite time light has had to travel to us within an expanding universe. Inside this observable sphere, astronomers estimate there are some 2 trillion galaxies. Each of these galaxies, in turn, is home to billions or even trillions of stars. When you calculate the total, the number of stars within our cosmic horizon is staggering, estimated at around 200 billion trillion. That figure is a 2 followed by 23 zeros. We also know from observation that the vast majority of stars host at least one planet. This suggests that the number of planets is likely similar, and perhaps even greater. The universe is teeming with worlds, more than we could ever catalogue, and certainly more than we could ever visit, even with infinite time and technology. On the largest of scales, the universe exhibits a distinct structure. Galaxies are not sprinkled randomly throughout space. They are organized into clusters, which are gravitationally bound collections of many galaxies. These clusters are themselves grouped into even larger assemblies known as superclusters. These superclusters are arranged into enormous, thread-like formations called filaments. which can stretch for hundreds of millions of light years. In between these cosmic filaments lie vast voids, enormous regions of space containing very few galaxies, which can also be hundreds of millions of light years across. The universe is in a state of constant expansion, with space itself stretching and carrying galaxies along with it. This process is not about galaxies moving through space, but rather about the space between distant objects expanding, creating more distance between them. For objects that are relatively close, this expansion is imperceptible, as it is easily overcome by other forces. The space separating the Earth and the Moon is not expanding in any significant way, because gravity holds them together. Likewise, the space within our solar system, and even within our own galaxy, is not expanding, as gravity keeps the planets in their orbits and the stars bound to the Milky Way. However, on grander scales, between galaxies, and especially between galaxy clusters separated by hundreds of millions of light years, this expansion becomes the dominant force. Distant galaxies are receding from us as the space between us continues to stretch. A key detail is that the farther away a galaxy is, the faster it appears to move away. This is not because the galaxies themselves are traveling at incredible speeds through space. They are relatively stationary within their own local cosmic neighborhood. The high recession speeds are instead the cumulative effect of the expansion of space over those vast distances. For galaxies that are sufficiently far away, the space between them and us is expanding faster than light can travel through it. This remarkable fact does not violate the universal speed limit. The galaxies themselves are not moving through space faster than light. They are essentially at rest in their local region, while the space itself expands so rapidly that the distance between us grows faster than a photon could cross it. It is akin to attempting to run on a moving walkway that is traveling backward faster than you can run forward. Though you are running at your normal pace, you are moving away from your starting point. This means there are regions of the universe receding from us so quickly that their light will never reach us, not in a billion years and not in a trillion years. There exists a cosmic horizon beyond which we can never see, not because the light has not had enough time to arrive, but because it never will. The expansion of space is carrying those regions away from us, faster than light can bridge the growing divide. We are fundamentally and irreversibly cut off from those parts of the cosmos. Given the immense number of stars and planets, the universe is 13.8 billion year history, and the fact that life arose on Earth relatively quickly once conditions were right, it would seem probable that life exists elsewhere. This could even include intelligent, technological life. Yet, we have never detected any evidence of alien civilizations. We have found no radio signals carrying messages, no background electromagnetic hum of alien technology, no laser pulses, no megastructures, nor any other signs of large-scale engineering. The universe appears to be silent. This puzzle is called the Fermi paradox, named after physicist Enrico Fermi, who famously posed the question of where everybody might be. The light year itself might hold part of the answer. The distances separating the stars are so vast that they create enormous, perhaps insurmountable, challenges for communication and travel. Our own radio signals, television broadcasts, and radar pings have been leaking out into space for approximately a century. These signals propagate at the speed of light, spreading out in an ever-expanding sphere. They have now reached every star within a radius of about 100 light years from Earth. While 100 light years is a tremendous distance by human standards, our Milky Way galaxy is 100,000 light years across. Our signals have therefore covered only a tiny fraction of our galactic home. We have barely announced our existence to our most immediate cosmic neighbors. Furthermore, these signals become progressively weaker as they travel. The farther they go, the more they disperse over an increasingly large area. By the time our television broadcasts reach a star just a few dozen light years away, they are so faint that they would be nearly impossible to distinguish from the natural background radio noise of space. Even with highly sensitive instruments, any alien civilization attempting to listen would require extremely powerful radio telescopes, aimed in our precise direction, at just the right frequency, and at the right moment to have any chance of picking up our faint transmissions. So, what does this all mean for us? And how should we perceive light years in our daily lives? For most people, the concept of a light year has no direct effect on their day-to-day existence at all. The 24 light-year distance to Proxima Centauri is not a fact that typically influences our daily decisions, such as what to eat for breakfast, whether to carry an umbrella, or how to navigate the morning commute. There is, however, a distinct value in occasionally stepping away from our immediate world to contemplate such scales, as it provides a profound perspective on our place within the universe. When you truly grasp that Earth is a small planet orbiting an ordinary star, that the next closest star is over 4 light-years from us, that our own galaxy holds hundreds of billions of stars, and that trillions of galaxies populate the observable cosmos, your viewpoint begins to shift. Whatever your personal problems may be, they unfold on a tiny planet adrift in an immense universe. That disagreement with a friend, the pressure from work, anxiety about what lies ahead, a feeling of disappointment or frustration, all of these experiences are confined to one small world. The nearest star is unconcerned with our troubles. The galaxy takes no notice. The universe continues its slow, grand evolution, entirely indifferent to the affairs of humanity. This reflection is not meant to diminish the significance of your experiences or to suggest that your problems are unimportant. Your life is deeply important to you, and that is what truly counts. Pain is still pain, joy is still joy, and love is still love. These are real and vital aspects of existence, regardless of the universe's scale. Yet, at times when life feels overwhelming, when stress or anxiety or worry takes hold, it can be helpful to remember the sheer scale of the cosmos. It can be grounding to recall that you are living on a small planet that circles an average star, all within a vast and ancient expanse. From that cosmic vantage point, our difficulties seem temporary, local, and small, not insignificant, but contained and ultimately manageable. There is also a unique beauty in understanding the concept of light years. When you look up into the night sky, you are seeing far more than simple points of light. You are seeing stars that are separated from you by light years of distance. You are seeing photons that have journeyed through the vacuum of space for years, or even centuries, just to reach your eyes. This creates a connection to those distant suns, a link that spans vast stretches of both space and time. You are an integral part of this universe, composed of atoms forged inside stars, now looking up at other stars and beginning to comprehend your place in the cosmic order. Every star has its own story. Some are young, just beginning to coalesce from collapsing clouds of gas and dust, their lives as nuclear furnaces just starting. Others are in their middle age, much like our own sun, steadily converting hydrogen in their cores in a stable, long-lived phase. And some are old, nearing the end of their existence after having used up their fuel. These ancient stars are destined either to become white dwarfs, cooling slowly over trillions of years, or to erupt as supernovae, scattering their constituent atoms across space to be recycled into new stars and planets. All of these stellar bodies are separated by light years, by distances so enormous that even light itself requires years to traverse them. The universe is a remarkably sparse place, characterized by tiny islands of light, separated by enormous oceans of darkness. And yet, these islands are interconnected. They are linked by light, by gravity, and by the fundamental fact that they are all composed of the same essential materials. They are made of atoms forged in the hearts of earlier generations of stars, which were then scattered, recycled, and reformed into new stars, new planets, and potentially new life. As our technology advances, our capacity to measure distances in light years grows ever more precise. The Gaia spacecraft, for example, is currently assembling the most accurate three-dimensional map of our galaxy ever created, measuring the positions and distances of over 1 billion stars. Future telescopes will enable us to see even farther into space. The James Webb Telescope is already detecting galaxies that are over 13 billion light-years away, and future observatories may push that boundary even further back, closer to the time of the Big Bang itself. We are also discovering more exoplanets with each passing year. As of 2024, the number of confirmed exoplanets has surpassed 5,000, with thousands of additional candidates awaiting verification. Many of these worlds are dozens or even hundreds of light-years away, and we are gradually mapping what exists across these vast distances. In the future, we might even dispatch robotic probes to the nearest stars. The Breakthrough Starshot initiative, for instance, proposes sending tiny spacecraft to Proxima Centauri, Even if such a mission were successful, it would still take over 4 years for any data from the probes to be sent back to us. Barring some revolutionary breakthrough in our understanding of physics, the light year will remain a fundamental barrier. The distances that separate the stars are simply immense, and the speed of light is finite. This is not a problem that can be solved. It is a fundamental property of the universe we inhabit. Understanding the nature of light years changes how we perceive our place in the cosmos. It also raises profound questions about the future of humanity and our relationship with the universe at large. These are not merely abstract philosophical inquiries. They carry real implications for how we approach space exploration, the search for extraterrestrial life, and the long-term survival of our species. For most of human history, the universe was conceived as being small. Ancient civilizations believed the stars were lights affixed to a celestial sphere, located just beyond the moon and planets. The entire cosmos was thought to be contained within a space that one could potentially reach with a high enough ladder. Even after we understood that the stars were distant suns, we had no real concept of just how distant they were. Whether it was a few million kilometers or a few billion, the numbers were beyond our ability to measure, and so they remained abstract and undefined. It was not until the early 20th century that we started to accurately measure the distances to stars and began to appreciate the true vastness of space. When Harlow Shapley calculated the size of the Milky Way in 1918, revealing it to be approximately 100,000 light-years in diameter, many astronomers were stunned. The universe was far larger than anyone had previously imagined. Then, when Edwin Hubble demonstrated in 1929 that the spiral nebulae were in fact distant galaxies millions of light-years away, the universe expanded once more, this time by orders of magnitude. Our perspective shifted from believing the Milky Way constituted the entire universe to realizing it was just one galaxy among potentially billions. Today, we know that the observable universe is 93 billion light-years across and contains an estimated 2 trillion galaxies. This is a number so large that it becomes almost incomprehensible, yet it represents a real, physical space that exists all around us. In every direction you look, if you could see far enough, you would find galaxies stretching away into the distance, more and more of them, until you finally reach the edge of the observable universe, the point beyond which light has not yet had enough time to reach us. This knowledge alters our perspective in a fundamental way. We are not at the center of the universe. We are not special in any cosmic sense. We live on a typical planet, orbiting a typical star, within a typical galaxy, in a typical region of space. There is nothing unique about our location in the cosmos. Imagine for a moment that you were transported across the cosmos, arriving in a distant galaxy billions of light-years from home. The view, remarkably, would be quite familiar. A panorama of galaxies stretching out in all directions, fading into the far horizon. The universe, it seems, presents a broadly consistent appearance from any location. This realization inspires a profound sense of duality. It is, on the one hand, deeply humbling, as it underscores just how insignificant we are on a cosmic scale. The complete saga of human civilization, every war waged, every empire constructed, every scientific breakthrough achieved has unfolded on a single small planet in a quiet corner of one very typical galaxy. From a grand cosmic vantage point, our existence is barely perceptible. We are much like microorganisms living within a single drop of water, wholly unaware of the immense ocean that envelops them. But at the same time, this understanding is incredibly empowering, for it reveals the extraordinary capabilities of the human mind. We deduced all of this. We developed the methods to measure these incredible distances and to comprehend our place within the cosmos. We engineered telescopes, spacecraft, and sophisticated mathematical models that gave us the ability to observe and quantify phenomena billions of light-years away. We may be minuscule, but we are also immensely capable. As conscious beings, we possess the ability to understand the very universe that brought us into existence, and that in itself is a remarkable thing. An appreciation for the vastness of a light-year forces us to confront the formidable truths surrounding space exploration and the future of humanity beyond our own world. The distances are so staggering that they might constitute fundamental barriers, ones that no amount of technological advancement could ever truly conquer. Consider for a moment what would be required to send a human crew to another star. Our closest neighbor, Proxima Centauri, is 4.24 light-years away. With our current capabilities, the fastest probe ever constructed by humanity reaches a peak velocity of approximately 192 kilometers per second. At that speed, a journey to Proxima Centauri would take around 6,800 years. That span of time is longer than the entirety of recorded human history. A mission launched when our ancestors first developed writing would still be traveling through the void today, not yet having reached its destination. To make interstellar travel even remotely practical, we would need to travel substantially faster. Even if we could achieve 10% of the speed of light, a feat that would demand revolutionary new forms of propulsion far beyond anything we can currently construct, the trip to Proxima Centauri would still last for more than 42 years. That is longer than most professional careers, exceeding the typical time between finishing one's education and entering retirement. And this is merely the journey to the nearest star. The vast majority are situated much, much farther away. The engineering obstacles are truly formidable. Propelling a spacecraft to such velocities requires an immense expenditure of energy. The crew would need to be shielded from constant radiation throughout the long voyage. Life support systems would have to function flawlessly for decades, and then there are the psychological burdens of being confined to a small vessel for most of a lifetime, never to see Earth again, while journeying through empty space toward a destination that one might not even live to see. One proposed solution is the concept of multi-generational ships, which would be massive vessels capable of supporting hundreds or even thousands of people for the centuries needed to reach another star. The individuals who would eventually arrive at the new world would be the distant descendants of the original crew who began the voyage. They would have been born on the ship, lived their whole lives within its confines, and would finally reach a destination they had only known through stories. The vessel would essentially become a small, mobile civilization, completely cut off from Earth and developing its own unique culture and society during the long passage. But even these multi-generational arcs may not be a practical solution. The challenges are immense, from maintaining a perfectly closed ecosystem for centuries on end to preventing genetic problems that arise from inbreeding within a small population. There would be no guarantee that the descendants would still wish to complete the mission their ancestors had initiated. It is conceivable that after several generations, they might decide to turn around and attempt to return home. And if a disaster were to strike a critical system failure, or a plague that eliminated a large portion of the population, there would be no rescue mission on its way. They would be light years from any possible assistance. Others have suggested suspended animation or cryogenic freezing as a potential answer, placing the crew into a state of deep sleep for the journey and awakening them upon arrival. This approach would solve many of the inherent problems, eliminating the need for decades of life support, the psychological strain of long-term confinement, and the risk of the mission's objectives shifting over generations. However, we simply do not know if such a technology is even possible. Can the human body truly survive being frozen for decades or centuries and then successfully revived? The formation of ice crystals can cause irreparable cellular damage, and the potential effects on the brain and on memory remain profound, unsolved problems that may not have any viable solutions. The sobering reality is that human interstellar travel might just be fundamentally impractical, given the limitations imposed by the speed of light and the sheer scale of distances measured in light years. It is possible that we are confined to our own solar system for the foreseeable future, perhaps even permanently. This does not mean we cannot explore other star systems with robotic probes, but the human exploration of other stars may forever be confined to the realm of science fiction. The light year also fundamentally shapes our perspective on the possibility of contact with alien civilizations. If intelligent life does exist elsewhere in the cosmos, and many scientists believe it probably does, given the vast number of stars and planets, the immense distances might make contact impossible, even if both civilizations were to survive for millions of years. Let us imagine there is an advanced technological society on a planet that orbits a star 50 light years away. Much like us, they have developed radio technology and have been broadcasting signals into space for the past century. At this very moment, those signals are passing through our region of space. But after traveling for 50 light years and spreading out over an enormous sphere, they would be incredibly faint, To have any chance of detecting them, we would need to be aiming highly sensitive radio telescopes in precisely the right direction, at exactly the right frequency, and at the perfect time. The odds of this happening by pure chance are infinitesimally small. Even if we were to detect their signals, consider the sequence of events that would follow. We would be receiving a message they had broadcast 50 years in the past. If we were to send a reply immediately, our response would require another 50 years to reach them. This creates a 100-year round trip for a single exchange of information. One could transmit a question and then die of old age long before an answer could ever be received. It might be your grandchildren who would hear the reply to a question you had asked. This dynamic fundamentally alters the nature of any potential contact. There could be no dialogue in the conventional sense, no conversation or negotiation in real time. Instead, any communication would more closely resemble a slow exchange of encyclopedic entries passed between worlds across the vast, silent expanse. Imagine one civilization broadcasting everything it has ever learned, its complete history, science, and culture into the cosmos, hoping another world might receive the transmission and reply in kind. Such an exchange would be less like a conversation and more like a form of cosmic archaeology, an effort to study the records of a distant society, records that are already decades or even centuries old upon their arrival. This entire premise rests on the assumption that both cultures survive and remain dedicated to the dialogue long enough for it to unfold. Our own species has only been transmitting radio waves for about 100 years. We cannot know if we will still be doing so in another century, let alone for the many centuries required for a back-and-forth exchange. It's possible that civilizations rise and fall on timescales shorter than the time it takes for light to travel between stars. We could one day receive a message from a society that became extinct ages ago, listening to the final radio whispers from a world that has long since fallen silent. There is also the deeply unsettling possibility that the universe is filled with civilizations, but they are all separated by such enormous distances that none can ever make contact. The typical distance between intelligent worlds might be thousands of light years. Across such a void, merely detecting another's existence becomes a near impossibility, rendering any attempt at communication futile. Each society would emerge in isolation. They would make their own discoveries alone, ask their profound questions to an empty sky, and eventually vanish, never confirming if anyone else was out there. One of the most significant consequences of grasping the scale of a light year is the stark realization of our own solitude. The gulfs separating the stars are so immense that meaningful travel or contact may simply be beyond our reach. This would leave every civilization forever confined to its own small cosmic island. Even if our own galaxy holds millions of technological societies, the average separation between them could still be thousands of light years. At that scale, communication becomes almost without purpose. By the time a message is received and a response is sent, thousands of years will have elapsed. The civilization that sent the initial signal might no longer exist. Their world could have been struck by an asteroid, or perhaps they destroyed themselves in a war. It's also possible their star became unstable, making their planet uninhabitable. A reply would be a message sent to ghosts. What emerges is a portrait of a cosmos potentially rich with life, perhaps even intelligent life, but where each instance is eternally isolated by the sheer vastness of space. Every culture develops on its own, asks its questions on its own, achieves its breakthroughs on its own, and in the end, disappears on its own, never knowing if other minds existed under other suns. There is a deep melancholy to this thought. We have evolved as social beings. Connection is fundamental to our human identity. We form communities, we share what we learn, we collaborate on great works. The idea of being alone in the universe, or of being surrounded by others we can never meaningfully reach, is a profoundly lonely one. And yet, there is also a unique beauty in this perspective. It implies that every civilization that does manage to arise is incredibly precious. If we are alone, or effectively alone due to the impossibility of contact, then we carry a distinct responsibility. We become the universe's way of knowing itself, right here in this specific corner of space. The thoughts we have, the art we produce, the science we uncover, and the love we share, all of it is unique to us. We are not merely one civilization out of millions. We could be the only minds in our entire region of the galaxy, the sole consciousness for dozens or even hundreds of light years in every direction. This realization makes what we do more significant, not less. Every act of compassion, every new discovery, every work of art, every moment of joy or shared understanding, it all has weight. This significance comes from the fact that it is happening here and now, and may not be happening anywhere else nearby. We may be isolated, but we are also important. We are small, but we are also precious. In the grand cosmic scheme, we may seem insignificant, but we are also irreplaceable, because there may be no one else like us for light years in any direction. Tonight, we have journeyed through the immense scale of the light year. We have considered its meaning, its measurement, the distances it describes, and what it reveals about our place in the universe. We have traveled from the familiar scales of our daily lives to the nearly incomprehensible expanses of cosmic distance. A light year represents 9.46 trillion kilometers. It is the distance that light travels in a single year, moving at a constant speed of 300,000 kilometers per second. This is the unit astronomers employ because familiar terrestrial measurements like kilometers become completely impractical when grappling with the distances in space. When measuring the separation between stars and galaxies, you need a unit vast enough to keep the numbers manageable, yet still grounded in something physical and observable. The closest star to our own Sun, Proxima Centauri, is 4.24 light-years away. This is our nearest stellar neighbor, yet it remains so distant that our current technology would require thousands of years to make the journey. Our own galaxy, the Milky Way, measures approximately 100,000 light-years from one edge to the other. To traverse our home galaxy at the speed of light would take 100,000 years. The observable universe itself spans 93 billion light-years across and is estimated to contain 2 trillion galaxies, each one home to billions or trillions of stars. When you gaze up at the stars in the night sky, you are not seeing them as they exist in this moment. You are seeing light that has journeyed for years or centuries or even millennia to finally reach your eyes. You are, quite literally, looking into the past. Sirius, the most brilliant star in our sky, is 8.6 light-years away. The light you see from it left that star 8.6 years ago. Betelgeuse, the red supergiant in the constellation Orion, is situated about 550 light-years from us. The light from that star began its journey during the Renaissance, over 5 centuries ago. The light year fundamentally links distance and time. It reveals them not as separate ideas, but as unified aspects of a single concept, space-time. The speed of light is a fundamental limit built directly into the structure of our universe. Nothing is capable of traveling faster than light. This is not some technological barrier that we might one day surpass with superior engineering. It is an absolute law of physics, a direct consequence of the way space-time itself functions. This means that distances expressed in light years are not just spatial gaps, but also real obstacles to communication and travel. The stars that are light years away are separated from us not only by an expanse of space, but also by an expanse of time. Even if we could travel at the speed of light, a feat forbidden for any object with mass, a journey to even the nearest stars would still demand years of travel. To reach other galaxies would require thousands or even millions of years. The universe itself is not static, it is expanding, and that expansion is gaining speed. A mysterious influence we call dark energy is responsible, pushing the universe apart at an ever-increasing velocity. Because of this, distant galaxies are receding from our vantage point, as the very fabric of space stretches between us and them. In the distant future, billions of years from now, our perspective on the cosmos will be profoundly different and far more empty. More and more galaxies will be swept beyond our cosmic horizon, carried away by the expansion of space so rapidly that their light can no longer bridge the gap to reach us. And yet, despite these immense distances and the fundamental limits they impose, despite the profound isolation implied by the light year, what we have learned about the universe is truly enormous. We have charted the positions of billions of stars, measuring how far away they are with ever-improving accuracy. We have identified thousands of exoplanets in orbit around other suns, and some of them show potential for being habitable. We have gazed upon galaxies billions of light-years away, effectively looking back in time to see them as they were in the universe's infancy, not long after the Big Bang. The light year has been the essential instrument for this exploration, allowing us to measure these cosmic scales, map the universe, and situate ourselves within it. This brings us back to where we began. A light year is, by definition, the distance light travels in 1 year, a length equivalent to 9.46 trillion km. The number itself is so large that it challenges our very ability to comprehend it, a scale so vast it renders our own planet almost infinitesimally small by comparison. However, a full intuitive grasp of this number isn't necessary to appreciate what it signifies. You can still appreciate that the universe is vast, far beyond our ability to fully grasp it on an intuitive level. You can appreciate that the light from faraway stars has journeyed for years, decades, centuries, or even millennia to arrive in your eyes tonight. You can appreciate that we inhabit a tiny corner of an enormous cosmos, on a small world circling an ordinary star in one of countless trillions of galaxies. There is something profoundly humbling about truly understanding light years and the scales they represent. This knowledge reminds us of just how small we are within the grand scheme of things. It shows us how brief our individual lives are when compared to cosmic timescales. It reveals our deep isolation in space, separated from our closest stellar neighbours by distances that would require thousands of years to cross with any technology we can currently build. It puts our own concerns and worries into a new perspective, showing us that from a cosmic viewpoint, the things that seem so important in our daily lives are ultimately temporary and local. And yet, there is also something deeply empowering about this same knowledge. We are the species that figured this out. Despite being small creatures on a small planet, we have successfully measured these incredible distances. We have come to understand our place in the universe. We built telescopes and spacecraft, and we developed the mathematical frameworks that permit us to see and comprehend objects billions of light years away. We are tiny, and for now, we are confined to this one small world, but we are also remarkably capable. We are conscious beings who can understand the very universe that created us, who can look up at the night sky and comprehend the nature of what we are seeing, who can contemplate distances measured in trillions of kilometers and time spans measured in billions of years. From this cosmic perspective, you are, in a way, insignificant. Your own life is a brief flicker, perhaps lasting 80 or 90 years if you're lucky, inside a universe that is 8 billion years old, and will continue for trillions of years more. You exist for just the blink of an eye on a small planet that orbits an ordinary star. But the intriguing detail is that you are also remarkable in your own right. You are made of atoms, forged in the very hearts of stars that died billions of years ago. Their matter was scattered across space and eventually recycled into new stars and planets, and ultimately into you. You are quite literally made of stardust, the product of cosmic processes that have been operating for billions of years. In a very real sense, you are a way for the universe to know itself, to understand its own structure, and to appreciate its own vastness, beauty, and complexity. So, the next time you find yourself looking up at the stars on a clear night, remember what you have learned. Those points of light scattered across the darkness are not just lights. They are distant suns, massive balls of fusing hydrogen. Each one could potentially be the center of its own system of planets and moons. They are light years away, separated from us by distances so vast that the light now entering your eye, the photons that traveled across space to reach you, has been on its journey for years or centuries. It is a humbling thought that some of that light began its journey before you were even born. Some of it left its star before your grandparents were born. You become connected to those distant stars across the vast expanses of space and time, linked by the light that has crossed the cosmic void just to reach you. The universe is, without a doubt, large beyond comprehension. You are small, a single person on a single planet, but you are here, and you can understand, at least conceptually, if not intuitively, what a light year really means. You can grasp that the universe is measured in these vast units, that space is filled with distances that dwarf anything in human experience, and that very understanding, that ability to comprehend your place within the cosmos, is what is truly extraordinary. It is what makes us human, what separates us from all other life on Earth. We have the capacity to contemplate infinity and our own smallness simultaneously. We can feel both humbled and empowered by the same knowledge. And perhaps that is the most important thing to take away from this understanding of light years. Not just the technical definition, not just the mathematics of 9.46 trillion km, but what it means for us as a species, for our future, for our place in the cosmos. We stand at a truly unique moment in our history. We are the first generation of humans to truly understand the scale of the universe. Our distant ancestors looked up at the very same stars and wondered about the same deep questions, but they simply did not have the tools or the knowledge to measure the answers. They could not have known that the stars were distant suns. They could not have known that those suns were light years away. They could not comprehend the vast distances that separate us from the rest of the universe. But we can. We have now measured these incredible distances. We have calculated them with precision. We know that Proxima Centauri is 4.24 light-years away. We know that the Andromeda Galaxy is 2.5 million light-years away from us. We know that the observable universe itself stretches 93 billion light-years across. These figures are not products of speculation or approximation. They are precise measurements, the result of decades devoted to careful observation and rigorous calculation. This knowledge has a way of changing us, as it must. When one truly absorbs the reality that reaching the nearest star would require thousands of years with our existing technology, a shift occurs. When you grasp that the light from remote galaxies has journeyed for billions of years just to arrive at your eyes, your perspective deepens. Comprehending that we might be fundamentally marooned by the sheer scale of cosmic distance alters how we see everything. It has the effect of making our own differences seem smaller. The subjects we debate, the borders we meticulously draw, and the conflicts we pursue all unfold on one solitary, tiny planet within an immense cosmos. We are all here together on this small world, separated from our closest stellar neighbors by distances that can only be expressed in light years. From that vantage point, the things that divide us seem far less important than the commonalities we share. This realization also makes our existence appear exceptionally precious. If we are alone, or effectively so, unable to traverse the light years that lie between us and any others, then what we do here carries enormous weight. It is possible we represent the only consciousness in our entire region of space. We may be the only minds capable of contemplating the universe and achieving an understanding of what is being seen. We might be the only beings who can create art, uncover scientific truths, and experience feelings of love, compassion, and wonder. That possibility bestows upon us a profound responsibility. It suggests we must act as careful stewards of this planet, this small island of life adrift in a cosmic ocean. It implies a duty to preserve and protect the knowledge we have so painstakingly acquired and the understanding we have developed. It means we are called to think in the long term, looking beyond the next year or decade to the next century, the next millennium, and the enduring future of humanity among the stars. The light year, then, is something more than a unit of measurement. It is a powerful reminder of our place in the universe. It reminds us that we are part of something indescribably larger than ourselves, but also that we possess a unique and precious quality within that vastness. It is a reminder that the stars are at once incredibly distant and intimately connected to us through the light that bridges those cosmic distances. Every time you allow your gaze to drift up to the night sky, you are participating in an act that is both ancient and profound. You are seeing across light years. You are looking directly into the past. You are witnessing the universe in its full glory. And you are an integral part of that universe, constructed from the very same atoms, operating under the same physical laws, and connected by the same fundamental forces that govern everything from the smallest particle to the largest galaxy cluster. This is what a light year truly signifies. It speaks not just of distance, but of connection. It represents not merely isolation, but a sense of belonging. It highlights not just our smallness, but the deep significance we hold within that smallness. Our exploration of space and time concludes for now. Good night, and perhaps, from now on, you will never look at the stars in quite the same way again.